Alright, hello world. I'm going to show you how to derive the Scholes PDE. I'm actually reviewing for an exam, and I was going to rewrite this down anyway, so I figured that maybe I'll do it this way and maybe it helps someone. I know there's a ton of videos already, and obviously, you know, an almost infinite amount of material online about deriving this, but I found that most of it sort of takes the hedging argument approach, and I know, or at least I think I know, maybe in the end this is really no different, but I think I know a slightly different way to get there that is more intuitive for me, probably just because it's the first way that I learned, but maybe it would be more intuitive to you as well. So here we go. So we of course start out, it's the normal framework, so we have some kind of contingent claim, we'll call it phi, that's based on, of course, the maturity value of the underlying asset. Now take a pricing function, we'll call it f, that of course depends on time and obviously the underlying asset as well, and we'll say that we'll shorthand this to just say that this equals pi. Now we're in the obviously the Scholes framework, which assumes that the underlying is following a geometric Brownian motion, meaning that the differential of the underlying asset has some constant drift alpha times, of course, the underlying times the time increment plus a diffusion coefficient, another constant, sigma, again times the underlying, and then times a increment of a standard Wiener process. I'll use W to denote Wiener process. It's obviously also known as a Brownian motion. I'm going to choose to use W because in other problems I use B to denote a bond. But anyways, with this, now think, and also I like to use F instead of V because the way I derive it, I take V as a value process or a wealth process, and obviously W is already taken in the Wiener process. But anyways, this is a lot of irrelevant details. Anyways, so take a value process, or or a wealth function of V that is equal to, we'll call a variable H. Sorry about that. Let me redo that. H superscript S at time t, and this denotes the number of shares you have in the underlying asset S times st plus, and we'll do another H superscript pi time t times, of course, pi. So this is just a very simple. All it's telling you is that the value of your portfolio, a portfolio based on the underlying asset and the option pi, is obviously just a product sum of the number of units you have of each one times the value of said units. So think about this now in terms of the differential of this wealth process, d of vt. That's a d, by the way, is equal to we're basically just going to turn st and pi into differentials themselves. So it's the same idea. It's the shares in the underlying asset times, times the change in the value of that underlying asset. And then same idea over here. Again, you have the shares in the option times the increment of that option. Now, another way to think about, or not another way, just this is equivalent to, if you think about what is H, the number of shares, what's another way to think of it? Well, think of the total value you have invested in the underlying asset or the option. It would be essentially the value of the entire portfolio times the weight. So let's take the stock first as an example. So it's the value process times, we'll say W superscript S to denote the weight of the underlying asset. So that would be the total amount of money that you had invested in the underlying asset. And then if you wanted to get back to the shares, you would do what? You would simply divide by what that asset costs at that time. So that's H superscript S. And then obviously H superscript pi would be the same idea. You would just have the weight of you know, the value of the portfolio times the weight you had in the option divided by the price of the option. So the point of this is that you can rewrite the wealth process and kind of just also using, I don't even know what to call it, the way math works, where you can just kind of move the denominator around, where you would have D of VT equals the value of the portfolio times the weight of each asset times the proportional change in each asset. I hope I don't go off the page here, so let me erase this 1 second and write it a little bit smaller. So you could also think of the value process in this way. Now, from here, we will change focus for a second. Now think of applying Ito's lemma to our price function. Recall it was f of t and st. Now this is so, at this point, general that, I mean, you couldn't have a more direct application of Ito's lemma. It basically is Ito's lemma. You're going to have the differential of this is equal to, obviously, the first derivative, the first partial derivative with respect to t. I'm using the subscript to denote partial derivative with respect to, I forget what that's, I think that might be the Euler notation, versus the, so this is equal to, the partial f over partial t, which if I recall right, that's the standard Leibniz notation. But anyways, ft, excuse me, I can read that as well. So it's the partial derivative of f with respect to t dt plus the partial derivative of f with respect to s times ds, and then of course plus 1/2 the second derivative with respect to s times dst, excuse me, squared. Now, we know something in this equation already. We know dst, since we defined it in the problem formulation. It's given by the geometric Brownian motion. So we can fill that in. Now it's also important to remember, let's do a little ancillary calc, that ds t squared is of course equal to alpha s t dt plus sigma d, excuse me, sigma s t d w t squared. Now it's important to remember the Ito multiplication rules. I don't even know if that's what they're called, but it's just that idea that dt squared is effectively 0 and dt dwt is also effectively 0. And then obviously dwt dt the same thing. The only thing you're left with is if you have the dwt squared term, that becomes dt. So the point of this is that when we go back into here and fill in our dst, we will be left with df equal to f, so partial f partial d dt plus f s alpha t plus sigma s t w t plus, and I'm going to simplify a little here, it's just going to be plus 1/2 second partial with respect to s times sigma squared s squared dt. Because when you do when you effectively take this term and multiply it by itself again, obviously again the dt dt, dt wt, dwt dt, those drop out, they're effectively 0, and all we're left with is sigma st dwt times sigma st dwt. Sigma and st is, normal, they just get squared, but then again the dwt squared turns into dt. So with these dynamics for f, let's collect all the dt terms and obviously the dwt term, and let's do a little trick here. So we're going to take df is equal to, again, we would collect the dt terms, so alpha s t plus 1/2 fss ss sigma squared s t squared, come on, and this would all be dt plus, and I run out of room here, so let's move this down. Let's do plus down here, fs s t sigma dwt. Now, like I said, we're going to do a little trick here, and that's, let's multiply and divide everything by f itself. So we'll have that times f, and then we can say that divided by f, and then same idea over here, we can have f times it, and then divide this part by f. Now, let's take this term, and we'll call this, call it alpha, subscript f, and then we will take this term and call it sigma subscript f. So we can simplify the way we wrote that to be to be df is thus just equal to this is not going well. Alpha subscript f dt plus sigma subscript f dwt. Now, we also know that we're making the assumption that, or it's not an assumption, it's just the way that it needs to be, that f is equivalent to pi, because f is the pricing function, so, and then pi is the price, so it's obvious. But the point is we can interchange the f's in this equation above, so we can change those to pi's, and then what we can do is then divide by pi. So we can rewrite this as d pi over pi is equal to alpha subscript f dt plus sigma subscript f dwt. Alright, well, why is that important? Well, if you remember, we'll go all the way back up to the value process. You see that right in here, we have this term d pi over pi. Well, hey, we just figured out what that is, right? It's right here. Furthermore, what else do we need in this value process? Well, we need dst over st. Well, obviously, we have that too. It's the geometric Brownian motion assumption for the underlying asset dynamics. So we can go back and fill all this in now, so that our value process is going to be dvt. I'm not out of room here, so I'm just going to write dv equals v times the weight of the underlying times alpha s. It's going to be obviously st, but again I'm going to drop that to save a little room. You'll see that these terms are going to cancel anyways, so doesn't quite matter. All over s, like I said, so those cancel. And then I'll close that off for now, because then you'd have plus v, and then of course the option part. Remember, we just figured out that this d pi over pi, it's right up here, is equal to that alpha f dt. dt plus sigma f dwt. Alright, so this will simplify to the following. dv equals v times the, so basically here we're simplifying and we're collecting dt and dwt terms. So we have ws times alpha plus w pi times alpha subscript f dt. Let me clean that up a little bit. Plus v times ws sigma plus w pi sigma underscore f dwt, of course. Okay, so this is a very important step, very important equation here. So we know a few things here. We are constructing a portfolio of the underlying asset and the option, and the goal is to construct a riskless portfolio. Well, as the name suggests, a riskless portfolio has no risk. So this term that incorporates randomness needs to fall out. Well, how can we do this? We can do it by simply setting this to 0. Furthermore, not only does the riskless portfolio not have risk, it also should earn, by law of one price, or the arbitrage argument, it should earn the same as a riskless bank account. Thus, this drift needs to be equal to R for no arbitrage. So what we can do with these two ideas, that is the drift needs to be equal to R for no arbitrage. So what can we do with these two results? Well, we can cast a system of equations now, where we take, up here, we had the weight of the stock times alpha plus the weight of the option times alpha f equals to R. And then also we need the weight, the weight of the stock times sigma plus the weight of the option times sigma subscript f equals 0. And what else? We need one more thing. Obviously the weights should sum to 1. So we have this system of equations. Now we just need to solve it. This one is going to eventually lead to the PDE. So we're going to solve these two first. Obviously, the last one is very easy to manipulate. We quickly find that we can just say that the weight of the stock equals 1 minus the weight of the option. Filling this back into the second equation, you will thus get that, so we'll call this 1, 2, and 3. So this is 3. So we go to equation 2, and we find that 1 minus w pi times sigma plus w pi sigma f equals 0. This is the same thing as, let's see here, we have sigma minus sigma. We really need to invest, it looks like, in a better writing system here. Anyways, w pi plus sigma underscore f w pi equals 0. Alright, now we will factor out w pi. So we have w pi sigma f minus sigma. I'll move the other sigma to the other side for now, equals negative sigma. This is the same thing as saying that w pi equals negative sigma divided by sigma subscript f minus sigma. Let's get rid of the awkward negative numerator. So we can just say that w pi is equal to sigma over sigma minus sigma f. So there's our first weight figured out, very important. So now what we'll do is we did that by manipulating 3, putting it into 2, so we'll go back down to 3 to find the weight of S. So we know that Ws plus sigma over sigma minus sigma F needs to be equal to 1 again. Okay, so this is equivalent to Ws being equal to 1 minus sigma over sigma minus sigma F. So let's rework 1 as a common denominator, so we have sigma minus sigma F over sigma minus sigma F minus sigma over sigma minus sigma F. And obviously this is equivalent to Ws being equal to negative sigma subscript F over sigma minus sigma F. Again, we will get rid of the negative numerator to finally be led to the weight of the stock should be equal to sigma subscript F over sigma F minus sigma. So I'll just quick rewrite then what we got for pi before is sigma over sigma minus sigma F. So these are our two weights that we find for the stock and the option. Very important. Okay, now again, these are just the weights, and so far we've only been working with the last two equations in this system. So again, it's important now to solve the first one, and this will lead us to the PDE. So first, let me go back down here, just so we don't have to keep scrolling up. Remember, that one is that the weight of the stock. The weight in the stock times the drift alpha plus the weight in the option times this little formula we came up with, alpha subscript F equals to R. Okay, so let's fill in what we just found for the weight of the stock and for the weight of the option. So again, we have sigma F over sigma F minus sigma times alpha. Let's see here. Yep, just making sure. Plus sigma over sigma minus sigma subscript F times alpha subscript F equals to R. Alright, so let's work this a little bit. So first, to get the denominators the same on the left hand side, we'll say sigma underscore F subscript F, sorry, sigma F, wow, what was that? Sigma F minus sigma times alpha minus sigma over sigma F minus sigma alpha F equals R. So multiply both sides by sigma F minus sigma, so you get alpha sigma F minus alpha F sigma equals sigma F minus sigma times R. Okay. Actually, let me expand this out. So sigma R sigma F minus R sigma. Okay. So from there, let's gather the like terms. So you would have sigma F alpha minus R equal to, yep, same idea over here. You would have sigma alpha underscore f minus r. Now, this is obviously equivalent to saying that alpha minus r over sigma is equal to alpha underscore f minus r over sigma underscore f. Now, here we have another important result. What's going on here? So this alpha minus r over sigma should strike you as very familiar as the market price of risk, or the Sharpe ratio. So they're equivalents between the underlying and the option. So let's call this, we'll say that this equals lambda. So we have lambda equals alpha underscore f minus r over sigma underscore f. Now this is the same thing as saying that lambda sigma underscore f equals alpha underscore f minus r. So, running with this equation now, what can we do? Well, remember we effectively defined sigma underscore f and alpha underscore f in the beginning. So let's fill those back in. So what we have then is lambda times the first derivative with respect to s times s times sigma over f. So that was the formula for sigma underscore f equals, and then we have the formula for alpha underscore f, which was the first derivative with respect to t plus the first partial derivative with respect to s times alpha s t plus 1/2 the second, it didn't help, but whatever, the second partial spatial times sigma squared s squared, and again all divided by f. And I might run out of room there, so you'd obviously of course have minus r. Let's not forget that. Alright, so now at this point you might think that we're very far along and we still have this alpha here. That doesn't make sense, right? Well, you'll see eventually why it's okay. So multiply everything through by f, leaving you with lambda first derivative with respect to s, st sigma equals yes, f first derivative with respect to t plus s alpha s t plus 1/2 fss sigma squared s squared t minus r f. Okay, so doesn't look like a very good r. RF, okay, so yes. So let's move everything to one side, and note that we have common fs terms, or not common, we have two fs terms, so condensing those will finally leave us with the first partial with respect to t plus, and then we're going to have alpha minus lambda partial s t yes plus 1/2 second partial sigma squared s squared minus r f is equal to 0. Now, we know one more thing. We know what lambda is, right? We defined it earlier. We said that it's the market price of risk for the underlying asset. So, if we fill that back in, I'll do this alone, we would have alpha minus r. There's a mistake right here. There's also, excuse me 1 second, it's lambda sigma. Lambda sigma f s s t. Okay, so just doing this term, we would have alpha minus r over sigma times sigma. So we see these cancel, you'll see the alphas cancel, and then it just becomes plus r. So that term ends up just equaling r. So there we see we finally have first derivative with respect to t plus r s t first partial with respect to s plus 1/2 second partial of s sigma squared s squared minus r f equals 0. So that there then is of course the Black-Scholes partial differential equation with the drift set to r rather than the drift of the underlying asset alpha. So I hope this helped. Again, this is my first time doing this. I just decided it could be fun since I was already going to do it. So as you can see, I am working on pretty terrible OneNote software. So I apologize for the horrible handwriting. But next, I think I'll also do some videos about a way I know to solve this PDE, so to get the Black-Scholes formula that doesn't involve nasty integration. It'll involve a few tricks, if that's the right word to call them. That is the Gersonov theorem, so changing measure, and also the Feynman-Keck formula that casts the solution to a parabolic partial differential equation, which is what we have here, as a conditional expectation.